6 megahertz wide, how many bits per second can be sent if 4 level digital signals are used, assume a noiseless channel? And so using the Nyquist theorem, you guessing that?
Oh, because I just kind of, sorry, no worries. I'll have an extra. Okay.
Through the Nyquist theorem, we can sample at 12 million times per second. 4 level signals provides 2 bits per sample, so you get a rate of 24 megabits per second. Megabits per second. Number 9 is the Nyquist theorem true for high quality single mode optical fiber or only for copper? It's math, it's true for everything. 37, 3-packet switch network. Oh, this is the fun. No. Anyway, 3-packet switch networks, each contain N nodes. The first is a star, the central switch. The second is a bidirectional ring. And the third is fully interconnected with a wire from every node to every other node. What are the best, average, and worst case of transmission paths? Well, of course, for the star, it's going to be 2 hops for everything. For the ring, the best case is 1, it's next door. The average case is N over 4, which means it's halfway around. And the worst case is N over 2. N over 4 is a quarter way around, one way or the other. And then the worst case is N over 2, it's directly opposite. And then, of course, for a full mesh, it's 1, 1, 1. Use the white. That's, yeah, I think you're going to have to. Okay, I'm going to come back to 39. 40, in a typical mobile phone system with hexagonal cells, it's forbidden to reuse a frequency band in an adjacent cell. If 840 frequencies are available, how many can be used in a given cell? Well, each cell, and actually this one doesn't require the full amount. Each cell has 6 neighbors. So if the center cell uses the frequency group A, its 6 neighbors can use BC, BC, BC all the way around. In other words, only 3 unique cells are needed. Consequently, each cell can have 280 frequencies. Okay, this is a very famous math problem. Does anybody know what it is? No?
You told me about you worked with the guy who came up with it.
It's called the 4-color problem. There was a conjecture back in the 19th century that any planar map can be colored with 4 colors without the colors having to be adjacent. Okay, the problem stood into the 1970s when Haken and Abel, I took real analysis from Haken, solved it by using a computer to generate the 200 possible planar maps and then coloring. Okay, and actually what they did is they wrote a program to do this. And then to check the program, they actually printed out the maps in between the Haken family and the Apple family. They colored them all and made sure it worked. Haken was a real character. You'd see him bicycling into the university, and he looked like he was going to fall over at any time we were going to lose him. You know, I mean, and the guy had a really thick German accent and a really dry sense of humor. And when we were taking class with him, at first class, it was like, he'd be going along and he'd be writing this stuff in a great monologue, and he'd crack this little joke or something, and we started looking at each other like, did he just crack a joke? Slowly we began to sort of figure out that, yeah, he did actually, he had quite a good sense of humor. Which in the math building at Illinois you could make use of, because the math building was a strange building. My first freshman year there, I had a class on the 4th floor. I finally went outside, counted the windows and said, okay, yeah, there is a 4th floor, now I'm gonna go find it. You know, and it was, turned out you had to go up one way and it was sort of a half floor, and then there were some stairs that went up. There were circular staircases, marble circular staircases that went all the way to the basement. Friends of mine used a bicycle box to race down. You know, it was a strange building. 49, a cable company decides to provide internet access over cable in a neighborhood consisting of 5,000 homes. The company uses a coaxial cable and spectrum allocation allowing 100 megabits per second downstream bandwidth and for cable to attract customers. The company decides to guarantee at least 2 megabits downstream bandwidth to each house at any time. Describe what the cable company needs to do to provide this. Okay, so 2 megabits downstream guarantees each house at most 50 houses per coax. The cable company will need to split up the existing cable into 100 coaxial cables, each connecting them directly with a fiber node. And then in class, we analyzed, my problem is to go do the HDLC thing, and I'll pick that up somewhere else. But let's go back to number 30. Okay. Suppose that there are X bits of user data are to be transmitted over a K-hop path in a packet switch network in a series of packets, each containing P data bits, H header bits, and with X much, much greater than P plus H, which means we can ignore it. The bit rate of the lines is B bits per second, and the propagation delay is negligible. What value of P minimizes the total delay? Okay. What I'm really looking for here, and I don't expect you to, I don't expect you to be able to solve this, but I expect you to know how to solve it. So the question is, how do you solve this? What do you need to do to find the minimum? Anybody?
So I wrote like this: total data is equal P data bits plus H data bits, and multiply to let's go.
Yeah, but what's the big operation you're gonna have to do to find the minimum? Anybody? Too far back in the past?
Don't you want to make sure that it's minimized like buffering?
Okay, all right.
You mean reduction?
Huh?
Reduction?
No, you want to take the derivative and set it to 0.
Oh, derivative. Oh my
Right?
God.
This is basic calculus. Okay? In order to find the minimum of any function, remember the derivative is the slope of the curve at a given point.
Right.
So when so a derivative, setting the derivative equal to 0 means that it's either a maximum or a minimum. Okay? And so that's what you need to do. And here, I'll just sketch it out.
Professor, may I ask a question?
Yeah.
Here in the question, K-hop, my question is, from computer to the router, isn't hop 2?
Yeah.
So in this case, so we have 3 router, right?
No, you don't know how many routers.
But here, it says we have
You have K routers.
K routers.
K
So
hops.
I pretend to be, I have 4 routers, right? 4 routers.
Well, you can pray that, but that's not what the answer's all about.
No, I mean.
Let me, let me tell you a story. I like these because I got skewered by them myself. Okay? when I was a freshman taking physics, the physics TAs told us, look, guys, don't just, come up with the equation and plug in the numbers and do it. Reduce the algebra before you plug in the numbers. You'll get some understanding of what's going on here with physics. Of course, we were young engineers and we just had to get our homework done, right? So we just plugged in the numbers and did it. So they started giving us homework problems with no numbers and forced us to reduce the algebra. So I'm just passing the pleasure on. Okay. Now, let me sort of go through this. So the total number of packets needed. Total number packets is going to equal X over P, right? Total number of bits and the maximum length of the packet. So the total data plus header traffic. So data plus header is going to be P plus H times X over P. The source requires, so the source is going to require P plus H X over PB seconds to transmit these bits. Retransmissions of the last packet of the by the intermediate routers takes up a total of, so the last router is going to be K minus 1 P plus H over B seconds. Adding up the time for the source to send all the bits plus the time for the routers to carry the last packet to the destination, thus clearing the pipeline, we get a total time. So the total is going to be equal to P plus H X over PB plus, what was I missed before? P plus H K minus 1 over B. Now, minimizing this quantity, we want to take the derivative with respect to P and set it equal to 0, and that will give us that P equals the square root of HX over K minus 1. Okay. Now, I don't care about getting that. If he counted you wrong for that, let me give you all credit for it, because I just want to know if you knew how to get it, that you needed to do a derivative.
Can you explain what you just did?
Can I draw the question, my question?
Yeah.
I mean,
Well, no, wait. Okay, so this is what it takes to send all the bits.
I found the answer, but when I try to apply it in reality,
Yeah.
it doesn't work. I don't know where I made a mistake.
Okay.
So we have 4 rows, right? 1, 2, 3, 4.
Okay.
This all of them rows. And we have 1, 2, 3 hops. K hops, right?
Yep.
Hops. And we have
Wait. What?
K minus 1. Oh.
a hop. I
A
mean,
hop, right. Hops.
hops. And we have a computer here. Right?
Yeah.
So in this case, this between the computer and routers, do I have to calculate as a whole?
Yeah.
Or it's called only, I mean, all between routers?
Yeah.
Because, for example, I did like this. I have from 1 to 10 bits per second.
Yeah.
So
So
is this, I mean, I don't know, is this helpful for everyone? I'm just, what are we talking about?
Yeah, no, we don't need, can we do this?
Yeah.
We gotta get through stuff when we're already at that. Come up to me at the break, and I'll show you how we
Okay.
get the algebra. Okay, I don't, yeah,
So I just wanna raise, so like this problem, like I was not even close. And I think it was, we didn't go over it at any point beforehand.
well, no, we don't need to go over it. I mean, it asked how, all I wanted to know was, how do you find the minimum for this function?
Right, but
You had to arrive at the function first.
No. All you, as soon as you saw minimize to get the result, you knew you had to take the derivative. Whatever it was, you had to take the derivative,
how would we know that?
because you took calculus.
But we've never discussed calculus before.
That doesn't matter in this course. This is an engineering course. It is not self-contained.
No, I mean, we would have to have, taken the derivative of what,
Whatever function you came up with, you were gonna have to take the derivative and set it equal to zero.
yes, so you had to get to that point.
Yeah, right.
And
As long
then-
as long as you knew you had to take the derivative, I was satisfied. That's all I wanted to know. Okay? Now, we'll never have to do derivatives again, but I just wanted to see who knew and who didn't know. Okay? I don't know, I'll have to ask the grade. You know, but no, I mean, this is, a fairly common thing. Okay, and, if you're taking a course this far into a degree, this is the kind of math you'll run into from time to time. Okay? With respect to the other one, if we do HDLC for the mechanism of policy, well, obviously for delimiting, you've got the flag character of 6 months in a row. For STD protection, there's a CRC of either 16 and 32. Sequence numbers are used to keep it in order. Loss and duplicate protection uses the sequence numbers. And there's a data transfer command and some other commands. Flow control is a sliding window of fixed width, which is usually 7 or 8 or 7 or some other number, but usually 7. Okay? You're reading. All right. Yeah, so tonight, we're going to go through routing and the network layer. We've worked up to that point. Okay, so we're gonna divide this into 2 parts. It says here, the next 4 lectures are probably the most important in this class. We're gonna be covering routing, the traditional network layer, naming and addressing, and then the transport layer, which goes on top of all this. And there's no way to do this without some forward references. So bear with me. We're gonna have to talk about addresses before we really talk in detail about addresses. And we'll be talking about stuff in the network layer as well. And, actually, this lecture is the last lecture that will be on the midterm. Okay, everything from here back will be this fair game for the midterm. Okay. Now, if you remember, we got to this point where we were doing IPC on the cheap, where we wanted to get rid of all those directly connected lines. And we said that we'll have to have a system that does relaying, and we'll have to have something that figures out a forwarding, something that generates a forwarding table, so when a packet comes in, this forwarding process can look at the address and say, is it mine or is it go somewhere else? And if it goes somewhere else, which port of mine does it go out on? And so we'll need names for all those, and we'll have to put addresses on the front of our packet now. It keeps getting longer.
This is, the, router application.
Yeah, yeah. And so, you know, we're gonna look at how all that works. So we're gonna look at a whole bunch of things here. We'll put off looking at routing for mobile hosts and stuff until later. We wanted to get some other stuff in for that. So, you know, basically, we've replicated our basic, you know, IPC model here with error and flow control and stuff, and the data link protocol here. And stuff is coming in, it's gonna now look like this with addresses, ports, and we're gonna have something here which is gonna generate a forwarding table for us so we know where to send stuff. Now, why do we do routing? Oddly enough, we don't do it to determine the route that DDU is going to follow, but to build a forwarding table of next hops. All we want to know is, where do we send it next? So here's what we do. Each router exchanges routing information with others. They all execute the same algorithm with what we hope is the same data. We hope they all get similar results for what the optimal route would be through the network for some value of optimal. And then the routers build a forwarding table of where they are supposed to send their packets next on, and you know, that are in that solution. And if all goes well, the packet will indeed follow that path. Okay? Now, if the data is, if they don't all get the same data because of the asynchronous in the network, very bad things can happen. You can get routing loops.
So each router really only cares about, let me just get rid of this packet. On
That's
the,
all
on the
he
correct,
cares
on the,
about.
to the correct person.
Right.
Correct
That's
other
all
router.
he cares about. Okay? Now, what we're relying on here, so taking routing apart, and actually calling these routing protocols is a misnomer. Everybody in the industry calls them routing protocols. They really aren't. What they really are is a protocol for creating and maintaining a replicated database. Okay? So, first thing we have to do is update multiple copies of the database with multiple sources for the same information, determining the connectivity and finding the routes based on that data. Choosing the routes based on some sort of metric. You know, some weights that we put on the paths or the arcs in the graph. And then create a forwarding table. Basically, there are three fundamental types of routing so far. Link state, which requires complete knowledge of the graph. Distance vector, which has partial knowledge. And then sometimes we use a hierarchical routing in hierarchical networks, okay, where we can actually use the address as where to go. There are other things, lots of things that we study, but most of them sort of are variations on these. So one of the conflicts we have to deal with, of course, is if we pick a you know, an optimal path, we want to be a little careful because we've got to get fairness, because you know, X could be sitting to X prime and essentially blocking, you know, the other guys who are crossing the path from from getting any data set. So, you know, we have to balance that fairness and optimality. And then one of the other things that we want to talk about, you know, we're gonna rely on is the optimality principle, which says, you know, we go back to graph theory, and we say that you know, we recognize that any subpath of an optimal path is optimal, which is why the routing algorithm thing works. Okay, so if every router calculates the optimal path from M, and then uses the next hop, then when it gets to the next hop, it's going to use the optimal path from there. Since since the subpath of an optimal path is optimal, it will follow the optimal path. Theory, if the data is all the same. But it may not be. So one of the algorithms we tend to use is Dijkstra's algorithm. This is the linked state algorithm for what we do when you know, this is the algorithm that requires perfect knowledge of the graph. Okay, now I'm going to go through the algorithm, and you guys may want to go back and look at the algorithm while I go through the example, which we'll do at the end. Okay, I'm using the thing from Stallings because I thought it was clearer than the one that was in Tannenbaum. So, okay, so we start off. We have a set of n vertices. S is the source vertex. T is the set of vertices so far incorporated into our solution. Tree is equal to the spanning tree for vertices in T, including edges on the least cost path from S to T for each vertex T. We want to construct a spanning tree here. In other words, a tree originating at this router that goes to every other node in the network. Yeah.
So as every router produces its own idea of what is fastest for
Absolutely.
it.
Absolutely.
There's
Absolutely.
not one that
No,
everybody's sharing.
no. No, this is a distributed algorithm. Okay, this is why bad things can happen if you don't all have the same data. All right? Okay, so we'll define W of ij as the link cost from the vertex of I to the vertex of j. W of ii is equal to 0. W of ij is equal to infinity if I and j are not directly connected by a single edge. Okay? W of ij is greater than or equal to 0 if for I and j directly connected by a single edge. L of n is the cost of the least cost path from S to N currently known. At termination, this is the least cost path from S to N.
Can you draw on the board and show us how it?
Well, we're going to do an example after we get through the
Okay,
algorithm.
okay.
First, we have to, you know, this isn't even the algorithm. This is just the definitions, right? Okay? That's why I said you may want to look at the algorithm while I go through the example. Okay? So initialization. We set T equal to tree, and we only put the source node as a member of the set tree. L of n is equal to W of S comma n for n not equal to S. Initial cost path to neighbors are the link costs. So we want to get the next vertex. So we want to find X, not an element of T, such that L of X equals the min L of J for J, not an element of T. Add X to T and tree. Add X edge to T incident on X that has least cost path. And if this is the last hop on the path, then we're done. But update the least cost path so that L of n is the minimum of what we currently had plus a new one for all n, not an element of T. If the latter term is minimum, a path from S to N is now a path from S to X, concatenated with edge from X to N. Terminate when all vertices added to T requires on the order of V iterations, number of vertices. At termination, L of X is associated with each vertex is the cost of least cost path from S to X. The tree is a spanning tree, it touches every node, and defines the least cost path of S to each other vertex. One step adds one vertex to T and defines the least cost path from S to that vertex. Running order is on the order of V squared. Okay. So let's take a look at how this could happen. So we start up here, and we're gonna do this from node. There's a little confusion. This is,
You can use the mouse to be more accurate because we're talking about specific nodes.
I'm not real good with it.
Okay.
Actually, I can do it this way.
Hey, perfect. Okay.
Yeah, so, fine. Okay, so we're gonna start with one, so this is one here, V1. The subscripts are the vertexes, okay? We've got three vertices that we can incorporate. This one to 4, okay, which is weight 1. This one to vertex 2, which is weight 2. And this one to vertex 5, which has, or vertex 3, I'm sorry, vertex 3 over here, which has weight 5.
So why is that 2 for that weight from V1 to V2?
Whatever it happens to be.
How is it assigned?
How is it? What would you like it to be?
Is this just a propagation delay?
Could be anything. Could be
Okay.
propagation delay, it could be Q length. Remember, they've exchanged information about what they
It's just a
think is-
generic graph. is what it's-
Huh?
It's just a generic graph.
It's just a generic graph with weights of the arcs. Now, you can assign the weights by whatever metric you want.
So it's
Okay?
some metric that was.
Some metric
Right.
is used. You might need delay, it might be propagation time, it might be Q length. Q length has been a popular one to use. You know, there are all sorts of things you could use, okay? So, the algorithm doesn't care, clearly, okay? So that says the one that's minimum here is this one. So we incorporate 4 in our tree. Now we say, okay, so where do we go from here? Well, now we've got, you know, this one at 2, this one at 1 to V5, and this one to V3 is 3, and so this one is going to be 2, this one is 2, so we're going to incorporate, so at this step, you know, we've got a little bit of a tie here, but we incorporate node 2. So we've already incorporated, yeah.
What is T?
Up here.
So instead of T, we're going from 1 to 4 to 2, or 1 to 2
Yeah,
to 4.
remember, we're constructing the spanning tree.
So we're choosing which next right now?
I'm sorry, what?
We're on V4, correct?
Well,
Oh, no, we're
well,
still at
we've
V1
added
going out.
We've added V4 to the graph,
Yes,
and so now our possible next branches to add are V2, V3,
or V5.
and V5.
I have a question. My understanding of the set is that order does not matter. It seems like we're going as, like, from V1 to
No,
V2.
remember it said, remember the equations are such that order does matter.
So why are we putting it in a set where eventually we're gonna have
Well,
all?
no, he just says that there's a set of vertices, right? And then the definition of what a vertex is, remember, it was, if they're not directly connected, it's infinity,
Okay.
right? Okay?
I'm still not clear why, when you go to V1 to V4, I get the number being the distance of one.
So the distance, the distance from 1 is 2.
Distance from which vertex?
From vertex 1.
0?
You've already moved on to that one.
Yeah, right. Okay,
Right, I get that.
and then from here is 2.
From where? Yeah, pointers off. Up from vertex 1.
The weight here is 2.
For the edge weight is 2, and then that node also has a 2 inside it, so we
Right,
add 2?
yes.
So it's 4 total?
Yeah,
Okay.
yeah. So we added 4 last time, so we're gonna add 2 this time. Okay, now we come down
Okay,
here.
no problem. I got it now.
We've added this one and this one,
Right.
okay? Our next possible abilities are to add 5, 3, and 6. So this is 1, these are gonna be the sum, so they're gonna be longer. So we add 5. Then we come over here, and we've got this one, and this one. The next one to add is either 1 or this one, so we're gonna add B3. Okay? And then the last one, we're gonna pick up B6, which gives us a spanning tree. So now, if you would see, the shaded thing is a spanning tree that touches all the nodes. And it's a minimal spanning tree, it's an optimal spanning tree.
I also have a question as it relates to homework. If they were saying that to make a spanning tree, it's possible that you skip a router if none of the ports are on,
Sure.
if it's a loop. This forms a loop, doesn't it? So
No.
No?
Nope, doesn't form a loop. Look at the shaded things.
Okay, gotcha,
The
okay.
shaded things, okay? Right, and what we're really gonna do with this now is create our next hop table,
Okay.
which basically says, if it's going to vertex 2, right, we send it on that port, and if it's going anywhere else, we send it to V4.
That's the table only for vertex 1.
That's the table only for
So
vertex
you
1.
really, oh no, he does need to know the other ones, he just needs to know which port to go on.
Right, exactly.
That's all he needs out of it.
Right. So we're doing all this calculation just to get the
Just come
next
up with
hop,
2 exit points
and
in
then
this case.
throw the rest of it away. Yeah.
For vertex 6, why does it say infinity in the top 3 and then 4 in the bottom 3? How do we, is it something where we can't determine it, so it's like a question mark, so just saying infinity?
I'm sorry, what? No.
For vertex 6, it has the symbol for infinity on the top 3 diagrams.
Oh,
And 5 does on the first one.
Yeah, so is it just
Oh,
because
yeah.
since we haven't accessed it?
we haven't
don't
accessed
know?
it yet.
Okay,
Right. Yeah, we haven't gotten out there yet. So it's, you know. Okay,
Maybe
so its total distance from 1 is 4.
Again, this is the shortest path, right?
Right. We didn't find that out until we got to here. Right?
gotcha, thank you.
Sure. Okay? That's how link state works. Okay? Now, the other one that we use is distance vector. Now here, we just exchange vectors of how far I think I am from everybody else with my nearest neighbor. Okay? And he gives me a vector of how far he thinks he is from his nearest neighbor. Okay? And from that, I build a table. Okay? And so I get,
This is using the last algorithm's results?
I'm sorry?
This is using the last algorithm's results?
No, this is
This is a
using
new
a
one.
different schema. The last one was called the Dijkstra algorithm. This is actually called Bellman-Ford.
Okay.
If you want to go look it up.
But that last one was for link sets.
Huh?
That last one we just went through was link sets, you can see the routes or at least the connections all the way.
Right. It needs the last one needs full knowledge of the graph.
Exactly.
Okay, whereas here we only need nearest neighborhood information. Okay? All right, so what are we gonna do? When we get these vectors, these are the 4 vectors that J received from his nearest neighbors. So J gets one from A, from I, from K, and from H. Right? And he says, okay, what's my distance? Okay, so my JA, his delay is 8. Okay, and what is his distance, to A? Well, from, with this vector, going through A, it's gonna be 8.
Where does that
Going
come
through
from?
I, it's gonna be 10 plus 24, or 34. And, H is gonna be 32, and K is gonna be 27.
Where's the 8 come from on the JA delay? The 8, excuse me.
H, right there.
No, the number 8, it says JA delay is 8. Where is that?
Oh,
coming from?
what do you mean over here?
First
No,
column.
No, it's
Here?
there,
First column.
yes.
This is his measurement of his distance from, J's distance from A.
That's a good
He
question.
measures that himself.
Jay did it.
And so he measures his distance to I and to H and to K. Okay? Right? So now he adds that, so the minimum of those is 8. So 8 goes there. So now if you say, okay, how do I get to B? Okay, so 8 plus 12 is 20. 10 plus 36 is 46. 12 plus 31 is 43. 6 plus 28 is 34. This is the minimum route to B, so I put a 20 there. Is my weight. And I'm going through A.
I have a question.
Sure.
I understand this Y column to A, B, C, D, I understand that to A, or to J, but why is J trying to get to specifically A, I, H, and K? Why are those destinations?
Oh, because they're his nearest
It's
neighbors.
directly wired.
He gets those vectors.
How
from
is
his-
he close? I understand I and K, but where, oh, okay, I see it, okay, sorry.
Yeah, they cross, the lines cross, they don't, they don't intersect.
Gotcha, okay, thank you.
Sure. Okay? And that's how this one works.
Missing one piece, but I think I visualized it. So that first column, which is saying J to A, right?
Yep.
With an 8-second delay or even though the second.
Yeah, that's his vector from A about what his distance is to everything else.
But going down that column with all the destinations, A, B, A through
Yeah.
L, right? I'm trying to figure out how you're getting to F or like F.
Well, no.
No,
You,
you're not.
you're trying to, you mean you're trying to reason how F becomes that number?
Yeah.
Well, you don't know. All he knows is that's what he thinks.
So if I'm at position J and I want to get to F based on the column.
Oh, based on that, then I'll come across here and do the same thing. 8 plus 23 is 31. 10 plus 20 is 30. 12 plus 19 is 41.
31.
And 40 and 46. So I believe, if I remember right, it was this go through I. You get to F.
So it's J, I.
How does K know the distance to F?
Because other people told him what they thought their distance was. Keep that in mind because we're gonna see the problem with this approach.
But they're all updating each other. I mean, when does it ever settle out and acquiesce into a
Well,
final?
after every exchange, it quote settles out, but it doesn't, that's, okay, keep that in mind, all right?
I have a third
So we're,
question
we're,
before
we're,
the next-
we're cool how it works,
Yeah.
okay?
Well,
Here's the problem.
kind of.
Called the count to infinity problem. Okay? Here's what happens. A has been down,
Has been what, down?
down.
Oh.
A comes up, says to me, I'm here, and it's real close. Right? So B says, okay, it's distance 1 or something, and he propagates that off and says, I'm distance 1 from A. Right? So C says, oh, I'm distance whatever B to C plus A is. Y. And so on. A goes down
Again.
again. Okay? Somebody sends a packet to A. He gets to B, B says, I can't deliver this. Okay? A's down. C said, hey, I can deliver it. I'm not that far from A. So B sends the packet to C. C sends it right back. Right? He goes, what? And updates his distance from A through C, to infinity. Right? So now, D says, oh, I can deliver to A. And you see where this is going to go.
So is these packets of which you're speaking right now, are these management routing construction packets only? They're not data packets
They're
yet?
not data packets, they're just routing update packets. Okay? So the problem with distance vector is it's quick to pick up on new nodes, but it's slow to recognize that a node has disappeared. Okay, in fact, it's slow to converge, period. Okay, now this was the algorithm we originally used in the ARPANET. And of course, as the network grew, we began to run into these problems. Okay, so, in linked state, what we do is we discover its neighbors, learn their network addresses, measure the delay or cost of each of its neighbors, construct a packet telling of all it has just learned, and send this packet to all the other routers. Compute the shortest path for every router. Now, this needs, sends a query on each point of attachment that it has, announcing itself, and needs to have estimates of delay, the metric, from each one. Now, that means that modeling a LAN, for example, means that we're going to have to make it look like that. Okay, because the LAN essentially makes all these nodes look like they're equidistant. Okay? We have to be careful about including load in the delay determination. Better to use delay as an estimate of distance, and then consider load separately.
This is another algorithm?
No, this is using Dijkstra.
Okay, good.
Okay. In addition, of course, the other thing we have to be careful about is we're computing the optimal here, and we may have a situation like this, which actually occurred in the net, where, because we had the East Coast and West Coast, right, called router flat, where, we say, we compute this, and C says, hey, I'm the best path. I'm lightly loaded, I'm the best path to the East Coast. Everybody sends everything through C. C's queues get long, he gets slow. Next router update, E says, hey, I'm lightly loaded. I don't have, I'm a good way to get there. So now everybody flips over and sends everything to E. Now E gets bogged down. And it just keeps flipping back and forth. And so, in some sense, we're getting above a certain level, right? So above a certain cost, we'll alternate back and forth between the two. Okay. And and basically now, they remember that back when they were doing this in the 80s, they were trying to be really efficient. And they didn't have a whole lot of resources. So remember, everybody's sending these routing update packets to everybody else. So they're including in them a sequence number, and then they're recording an age as well. And as this age, they'll in the table they create, they'll keep decrementing the age, and if it never gets an update, they'll throw it away. So this is the way things sort of disappear. So each router builds its picture of the delay to all the other routers. Routers use the age and sequence number fields to ensure that they use the right information and to curb the flooding, so that we don't have flood storms going on all over the place. Age is decremented with time and discarded when it hits 0. New information is forwarded on all links except the one it came in on. Duplicates are discarded. All updates are ACT. And notice that this whole thing, most of the stuff in this protocol is all about getting this database right. It's not about routing, right? And of course, you can guess what was going to happen here if this thing has problems. If we run into the updates get out of sequence or something, and you get conflicting information, you could end up with creating routing loops. So we need to distribute to everyone, use flooding, try and keep it under control. Only the forwarding new ones. If it's duplicate, we destroy it. If it's old, we destroy it. This still means that duplicates will be received, age is maintained with the information and decremented. When it expires, the link information is discarded. The flags indicate who is to forward info to who and who is to act. Once this is done, we can construct a picture of the graph and run the Dijkstra algorithm on it. Now, it turns out
How quickly does this thing have to go up, or just?
these are done in most networks about every 30 seconds. Unless of course, there's a router crash or something. Okay?
So that's its heart, right?
Yeah, it's not. Yeah, they're not done real frequently, obviously, we wouldn't want to. In fact, you probably get away with even longer than 30 seconds. Now, link state converges faster than distance vector, and to the same answer, which is good, right? And it avoids the count to infinity problem and is less likely to develop loops. Notice that neither of these algorithms use addresses. They use the names of the nodes, but just as names of nodes. Okay, now, I will later talk about addresses as location-dependent, but route-independent identifiers. You know, just like, you know, addresses on the city streets, they're location-dependent. However, link state's not going to scale. We can't be sending router updates to every router in the internet. You know, that's just not going to work. So what we do is we have a two-tiered routing scheme. We use link state in what we call intra-domain,
Right.
where domain is is sort of like my network. Okay? And then we use a inter-domain, something based more on distance vector, called BGP, around the whole network. Okay? So we do this in two tiers in order to make this work. There's hierarchical routing, which you know, shows up very rarely these days in hierarchical networks where you can actually use the address as an indication of the routing table. Then we have broadcast and also multicast. And here what we're trying to do is, when you want to send it to everybody, this, you know, in Ethernet, broadcast or multicast is easy. Because you send it down the cable, and it's going to pass all the stations, just by definition. But in a network, you've got a different problem. And so what you want to do is find the minimal spanning tree from the sender. And then when you come to a node with a branch, you replicate the packet. Right? So you may take this network over here at A and build a spanning tree like this or one like that. Now if you send from I, when it reaches F, we replicate the packet and send one to D and one to A. Okay, and similarly, you know, we send one down here to J and he replicates it to G and O, and so on. And that gives us full coverage. Okay, and of course the sort of variation on that is multicast. In fact, we can look at multicast as sort of the general case of broadcast, where we say, okay, we're going to define a set of nodes, and we're going to send the same packet to every one of these nodes in the set. Okay, and so to do that, we'll want to create a spanning tree that just includes those nodes. Okay, and that's what there are all sorts of algorithms for that. You have a bunch of things like this. Then you also have what are called multi-peer. Most of these are where you have one guy sending. Okay, most of these. Now, if you have everybody sending, you really don't want to do N or N-1 spanning trees. So what we do is what's called a core-based tree. We find the center of gravity, and we essentially send everything into the core, and then it's propagated out as a spanning tree from there. Okay. Now there are algorithms for this and protocols for this. One that's most known, CBT, core-based trees. actually picks what, makes a guess at where the center of gravity would be, and it essentially starts from that node.
What do you mean by center of gravity?
Well, everybody's gonna be sending, so what node is close to, quote, the middle?
So it's equidistant to all of them.
Right, that they would all be, say, closest equal number of hops to the center, so that everybody goes the same amount of distances.
Gotcha.
Then, of course, there's anycast, which is the flip of multicast, right? Given the set of addresses and a rule, the rule selects one member of the set. So, for example, send this to the closest one. Send this to the least lightly loaded one. Something like that. That's not really well done in the internet, and there's still a lot of sort of question about how to do that right.
Is it only because it's at a group level? It
I-
sounds like it's a standard process.
Well, it's sort of a thing of, it's more a thing of, do people want to adopt it? Because basically, somebody's gonna have to have a definition of the set and the rule and do it and figure out what's going on. And in fact, the whole internet thing is a little weird because they generalize off the Ethernet definition. Which, in Ethernet, as I was saying, a multicast address in Ethernet is an ambiguous address. Every station on the Ethernet has the same multicast address, and when the packet goes by, oh, that's one of mine, take it off, right? Well, you can't do that in a mesh network, right? So they actually, in the early tries of doing multicast, they were actually flooding.
Playing algorithm or playing?
No, flooding.
Okay, yeah.
Sending packets to every node, so they passed across every node in the network. Because that was the only way, which was silly, as far as I'm concerned, okay? But we'll get to it, Now, the truth about multicast, and it's amazing how little this has been thought about. First of all, multicast is of little or no benefit to the user. Okay? What it's doing is reducing the load on the network. The user needs to send a copy of this packet to everybody in his group. Okay? If the network can get away with sending fewer packets and still get them to everybody, hey, so much the better. I have leftover capacity. Right? Now, whether he passes that savings on to the user or not, that's his business. Just within the last couple of months, I've had someone on a ITU committee I've been sitting in on say, well, we really didn't do a good job of explaining to users why multicast was useful to them. And I said, well, that's because it isn't. You should be selling it to the providers. But, it was just, we're going to put this new feature in the network, it must be useful to users. They didn't think about it.
When you say into the network, you mean into routers that a company's buying in their in-house to use?
Yeah. Well, okay. If I'm doing a spanning tree, the user needs to send, he wants a multicast group, so he sends a packet to all these guys in the group. He needs to send in packets. Now, if the network can create a spanning tree and send less than n packets and still get them to all those people, right? Because it's going down the tree and it's only being replicated at the branches of the tree, right? So the whole network's not seeing all that load. Okay, so this is an advantage to the provider. He can support sending in packets to end guys without actually having to send in packets over his whole network. Right, and capacity. But it's worth is it worth the trouble? It requires a parallel routing scheme. This has been one of the reasons that they haven't really been doing it. Is ISPs are sort of a little nervous about what happens if I put this parallel routing scheme for multicast in alongside my unicast routing scheme. What effect are they going to have on each other? The user needs never be aware of multicast. You can make the API look like a unicast API. He doesn't have to know anything. The important thing is to distinguish, creating a multicast group enrollment from joining a multicast group allocation. If it's done right, it's easy.
Professor, what about IPTV, for example? They
Huh?
use multicast, IPTV, right? IPTV.
Yeah,
IPTV, is it used multicast?
I think he does it by just sending in copies.
So, what does it mean by copies?
You send in copies of the same packet to end destination, as opposed to using a spanning tree. Multicast addresses aren't really addresses. If an address is location dependent, and this is a set of addresses, how can it be location dependent? There's the members of the set are all over the place. In the internet, they are ambiguous in names, it's what I just said. A multicast address is the name of the set, such that the reference, the set returns all members. In any case, it's the flip side of multicast. So multicast is for all anycasts there exist. Anycast is defined by a set, a name for a set, and rules such that when the name is referenced, the rules apply to select one element of the set.
Any task one more thing for me to, isn't it just,
Anycast is I have a set of addresses
that's it?
and a rule.
And you send them still one.
And when someone refers to the name of the set, I apply the rule, select one member of the set.
So it goes out one at a time.
That's the only one it goes to,
Oh, it goes only to that?
only to that one,
Okay, got it now.
okay?
Thank you.
Right. So this is when you want to do, they send it to the nearest one. Send it to the least lightly loaded one, something like that. Okay? So, being the kind of obstreperous pieces we are, we decide that we just refer to this as whatever text. Because if you read this rule, so I apply the rule, and I don't get back all, and I don't get back one, I get something in between. Basically, been two ways of doing this, connection and connectionless. We'll talk about that. Now, the environment area is basically, this is where supposedly relaying is taking place. And so the packet's coming in and is being forwarded around through the network using the routing algorithms we just saw. The services are independent of the routing technology. The transport layer is shielded from the number, type, and graphical routers. Network addresses are available. He says the network addresses available. The transport layer use a uniform numbering plan. Actually, I don't believe, there's really no need for it to be available to the transport layer or to the applications. That's another point to talk about later.
So we've moved on from the physical layer.
We went, last week we were the data link layer, remember?
Okay.
So now we're up to the layer, what they call layer 3, right?
Yes.
Okay. We're gonna start with, now, there are two approaches to this. One is called virtual circuit. And in this one, we have, in fact, there was a little bit of discussion about this at the end of last week. So what we're gonna do is, before we send any packets, we're going to dedicate a path through the network for those packets. Now, this gives us this has an advantage in that rather than have addresses in the packet, in the data packets themselves, we have very short channel identifiers. So that, and each node, they look at the channel identifier and say, okay, this channel is mapped to this one. Just like you were doing a plug board, for an old telephone system. Okay, so you don't have to carry full addresses in there. You only have to carry, these channel identifiers, which are very short. Of course, this has the problem that should anything go wrong in the middle, you lose a line or you lose a node, you got to go back to the beginning and start over. Okay, so that's one way. Then we can have datagrams. Datagrams where the packet has a fully qualified address. Every router knows what to do with the address. And so now we can just start sending them, and if one of the routers or lines goes down, the router looks at it and says, okay, what's my overrun for this? And sends it that way. Okay? And not only that, but this can change from packet to packet. So in datagrams, every packet is forwarded independent of every other packet. There's no requirement that they all follow the same path. With circuit switching, they will all follow the same path. Now, this is Tannenbaum's comparison of the two. For addressing, datagrams each have a full source and destination address. In virtual circuit, each packet contains a short virtual circuit number. In fact, actually, they're flipped at every hop. State information, routers do not hold state information about connections. We'll come back to that. Well, there are no, that's true. It doesn't hold state information about connections. Each VC requires router table space per connection. Routing, each packet is routed independently. In circuit switching, route is chosen when the virtual circuit is set up, and all packets follow that path. Effective failures, none, except for packets lost during the crash, which will be retransmitted by the layer above. All VCs that pass through the failed router are terminated, and you have to go back to the start and try and set up a new virtual circuit. Quality of service, he says it's difficult. It's a little odd, but it's not that difficult. Easy if there are enough resources to be allocated. Basically, one of the problems with the virtual circuit stuff is that you're statically allocating resources per connection. And we know what happens when you do that. Congestion control, well, it's not that difficult if it's done right. And there's some good stuff, we'll talk about that much later. Easy if enough resources can be allocated in advance for each virtual circuit. If you've statically allocated the resources, you don't let anybody send any faster than what you've allocated, nothing can go wrong. Now, this was the big connectionless war. This was the technical side of what was really an economic war between the phone companies and the computer companies. Okay, this is, the phone companies wanted virtual circuits, the computer companies were much more on the datagrams, and they were having it out. And I mean, I've been in meetings where I thought people were gonna come to blows on this stuff. I mean, it was, yelling and screaming and pounding the table. The war created a bunker mentality that made it really hard, understanding hard. I mean, when everyone's just jumping on everything you say and being really, aggressive about it, it's real hard to explore the trade-offs in any kind of reasonable way. And very quickly, both sides sort of retreat into a bunker mentality of they're afraid to compromise on anything for fear there's something they don't see and they'll lose the whole thing. For years, those of us who were moderates saw it as extremes of the amount of shared state. Connections had lots of shared state, connectionless very little, but there really, when you said that, it said it very nice and everything, but when you said, okay, so what's in between? It was real hard to find or characterize anything that would be in between those two extremes. Later, it became clear that as traffic becomes more deterministic, connection-oriented should be preferred. And as traffic becomes more stochastic, connectionless should be preferred. So basically, as I move down and in toward the center of the network, I've got lots of traffic all going to the same intermediate points in the network. Well, why look at every header? Just send the stuff. Get it out of here. So as I often say, there might not be constant traffic between Lexington, Mass. And Lake Forest, Illinois, but there's constant traffic between switching centers in Chicago and Boston. Okay? And so between Chicago and Boston, sure, be circuit switch. What the heck? I filter all the packets I know are going to the same place, and then they're going to be spread out to the other centers. And in those sub-networks, I might be connectionless, but in the backbone, I might be connection-oriented. You know, so this is not a matter of religion. The choice, now, a lot of people will tell you, well, connectionless is unreliable. Well, kind of, but not really, okay? The choice of which one to use is a trade-off between static and dynamic resource allocation, not reliability or error control, as is so often said. Because if I'm getting good quality of service from the layer below, and the guy above me says, I want this quality of service, hey, I'm already getting it. Well, why should I do any extra work? Right? Do connectionless. It's simpler. Now, if the guy below starts to deteriorate a little bit, okay, then we may add greater functionality and go to connection oriented. The more deterministic, the more connection-like. The less deterministic, the more connectionless. So as one moves down the layers and into the background, we would expect that traffic density is going to increase, and you should become more connection-like. As one moves out from the backbone toward the periphery, traffic density decreases, becomes more stochastic. Connectionless is probably more appropriate. Of course, connectionless does have better resiliency and survivability. Now, the question here was to find a synthesis of this stuff. And I haven't talked about that yet, but there were a number of times in the ARPANET, and we'll talk about it later in the semester, where they took two things that really looked like oil and water and found a nice way to do them both at the same time. I haven't bored you guys with my favorite machine, the Burroughs 5500. There's a real simple example there of doing this. The Burroughs machine came out in 1964, and it was unlike any other computer built for a long time. It was 10 years ahead of its time. It was a zero-address stack machine when nobody else was doing stacks. It was a tagged architecture. The stack was not executable. Okay, it was descriptor-based with virtual memory. The lowest level language on the machine was Algol, which is like a nice version of Pascal. Actually, Pascal is a subset of Algol. Okay, there was no assembler.
I know what an assembler is. The rest of the stuff.
A tagged architecture means that every word has a few bits in front of it that you can't see. That says, is this data or is this code? And if it's code or non-executable, if you try and access it, or write on it, it falls. It was descriptor based, which meant if you indexed off the end of an array, it was a fault.
Okay.
You couldn't get out of your arrays.
Still can.
The whole 9 yards. As I said, the lowest level language was Algol, which was a block structured statically scoped language. Okay. The operating system was written in an extension of Algol, so it was in a high level language too. Right? This machine obeyed the principle of least surprise. If you knew how A worked and B worked, you could guess how C would work and you'd be right. I mean, it just would. In fact, the book on this, Organic wrote, he wrote one on Multics and one on this. And in the book, he says, it appears that they got everything right. Okay? And one of the cute things that I always point to, the power of architecture, a floating point word on the Burroughs machine had a sign bit, an exponent, and a mantissa, right?
What's the last component?
Yeah.
What was mantissa?
Just what any other floating point number looks like, right? This is the fraction part,
Okay.
right? All right.
Would you
Floating
not
point
need
numbers
to-
are. This is how floating point numbers are stored in your computer.
But with an exponent, it's notation.
Huh?
With scientific notation, the exponent, you don't really need any information of like what's beyond the decimal point. You just bring everything.
That is the decimal point. The decimal point, most of the time in these machines, if you had computer architecture, the decimal point's there.
Okay.
Okay? Most all computers have two word formats. okay? The boroughs only had one. That one. But instead of putting the decimal point there, they put it there. They put it there because integers were simply unnormalized floating point numbers.
Normalized.
I knew you were gonna say that.
I don't know what it means.
In all computers, the floating point number looks like this, and that bit is always a one.
Okay.
Okay, so it's scaled so that the exponent represents the decimal point being here.
Uh-huh.
Okay, so if you are going between integers and reals, you have to convert from one to the other.
Okay.
Have you guys had computer architecture?
Yeah.
In college.
Huh? Isn't this college? Okay, alright. Okay. So, but now by moving the decimal point to here, an unnormalized floating point number is an integer. And if you divide or multiply and it gets too big, it simply floats. So integers are a degenerate case of floating point. That's what I call sweet design. Okay.
I'm more of a Ferrari man, but I can see how you appreciate this.
Well, yeah, and also in the Burroughs machine, a procedure was a process was a procedure.
Okay.
So when you call a procedure, it builds up on the stack. The only difference between a process and a procedure is what it returns to. Procedure returns within the stack, a process returns to the OS stack.
Okay.
And actually, they coded the first version of the Algol compiler in Octal. Machine code.
Okay.
Bare Octal, numbers on cards. This is 64, right? When they got the compiler to compile itself, they had a ceremony on the parking lot and they burned the Octal. No going back. Okay. So we need to find a synthesis like this for connection. So let's look at this very carefully. What makes connection-oriented so brittle after a failure? Now, I've been working on this for a long time, trying to figure out what, I'd said remote, streams of shared state, but there was nothing in the middle. And so I was thinking about it one more time. I said, so what makes connection-oriented so brittle? Well, when there's a failure, nobody knows what to do. You gotta go back to the beginning and start over. Well, wait a minute. That sounds like they don't have enough state information to know what to do. Well, what makes connectionless so resilient to failure? Everyone knows how to route everything. Well, wait a minute. This sounds like connectionless has a lot more state information about how to route stuff than connectionless stuff, or connection-oriented does, which is just the opposite of what we've been saying for 30 years. Yeah, connectionless isn't minimal state, it's maximal state. The dumb network, people like to refer to the internet as a dumb network, because it's all connections inside. Ain't so dumb. Where did we go wrong in our analysis? Well, we were just looking at the data transfer part. We weren't looking at everything that was going on in the layer. It was like doing a conservation of energy problem and getting the bounds on the system wrong. That's what we were doing. The amount of state is about the same, although where it is different, and the amount of replication is different. We have been distributing connectivity information to every node in a layer, but we've insisted in distributing resource allocation information only on a need-to-know basis, in other words, connection line. So we do routing, in a distributed manner, but we always revert to a connection node when we want to do resource allocation. So what do we know about this? First of all, connectionless is a function of the layer. It should not be visible across the layer boundary. In other words, you request a level of service, and the layer decides what it has to do to provide that level of service. If you can get away with doing it with connectionless, then that's connectionless. connectionless is characterized by maximal dissemination of state and dynamic resource allocation. Connection-oriented mechanisms attempt to limit dissemination of state information and tends towards static resource allocation. Applications request the allocation of communication resources. The layer determines what mechanisms and policies to use and tends towards CO, connection-oriented, when traffic density is high and deterministic, and CL when traffic density is low and stochastic. Similarly, PDU size should increase as we move down to and toward the backbone. In other words, as we're moving toward the backbone and traffic density is getting higher, we want to be switching more stuff less often rather than less stuff more often. All right, so we would want PDU sizes to get bigger. Internetworking. Networks differ, different technologies and stuff, and so we have to figure out how we're going to hook them all together. The collection of subnetworks, we have a bunch of collection of subnetworks here, and we need to hook them all together somehow. And they can differ with all these kinds of parameters and all sorts of stuff here. And, all, across the map. And so we have to figure out. Now, basically, there were two ways of doing internetworking, historically, as we figured out. First, there was a datacom approach, which was to do protocol conversion at the boundaries. In other words, just hook them together and convert from one to the other. This gets ugly, mainly because, first of all, you're generating an n-by-n problem, right? If you've got m kinds of networks, then you've got an m squared different conversions to make. And I don't know if any of you have ever run a device driver that did it and tried to emulate another device. But that stuff gets messy real fast. It's the worst kind of code you can ever have to write. The layered approach, on the other hand, provides a common layer across all of the other technologies, and essentially has them support the services of that common layer. That way, you only have an n-by-1. Every network has to do what it has to do to support the common layer, and that makes the problem a little easier. This implies that there is a minimal level of service required by the communication layer. And I think I said this early in the previous lecture. Everybody talks about the service that a layer provides up. Just as important is the service that the layer requires for the layer below. Because if you try and roll in a layer below that is flakier than what that layer was designed to deal with, then you've got a problem. So the phone company types chose the datacom approach. Basically the same as how the PSTN with the phone company worked, so that made them feel quite good. Retains their traditional datacom beats on the string model that they're familiar with. They were interconnecting relatively similar network types at the time, so it seemed like a pretty straightforward thing to do. And also, they didn't want to have a transport protocol, which we'll get to a little later. The transport protocol was going to relegate them to a commodity business, which they didn't really like. The research people said, no, let's do an overlay. Okay, let's build a common layer over the top and have different networks below it. And they assumed that there would be a wide variety of potentially very different networks, and this would be a much better, simpler way of going about it, rather than trying to do all the complex translations that might turn up. Here, layers are a locus of distributed shared state, as I talked about in the first lecture. And are cooperating to do resource allocation. Now, this is a distributed computing model. This was rediscovered a decade later when analyzing the network layer for OSI, and they had a problem of what happens if I have a high-quality network on two low-quality networks. I need some way to bring it up to snuff. And so they said that we will subdivide the network layer into 3 sublayers. This is what the native thing provides. This is the common layer we want to have, and if we need to do something to bring it up to snuff, we've got this thing in the middle.
So is this one of the things that they cut when they were going from 7 to 5?
Yeah.
Okay, no.
Well, actually, this is 75. 1975.
No, 7 to 5 when they're going to OSI. From,
Oh, yeah.
Okay.
Well, actually, this was going from 7 to
More than
5,
seven.
6,
Okay.
depends on how you want to count. And so you end up with something like this in the lower layers. Now let's take a look at what we've got for real. Okay? Here's IP. This is what an IP protocol header looks like. Okay, what do we got? Well, we got a version field. We've got we've got a header length field of 1 byte. There's a byte. Yeah, no, it's half a byte. Type of service field, total length 16 bits, a packet identifier, a fragment offset, and then 2 bits here. One is the don't fragment bit, DF, and one is the more fragment bit, which is how we're going to do fragmentation. Now, we're going to go through an example of fragmentation in a minute, but what we're going to have to do here is we're going to have each packet's going to have an identifier, and then we're going to have how many bytes it is from the beginning of that packet.
So this is every layers?
No, this is IP.
All,
This is just IP.
how do you fit all of that into one?
This is 32 bits wide.
Yeah.
These are the fields in the header. This is what every IP packet looks like.
Yeah, he's saying though, there's multiple rows per bit.
So if you have like, what is that, 4 bits per version,
Yep.
that will overlap with the bits for identification and time?
No, it doesn't overlap. This is another row, another 4 more bytes. The header is.
Wait, so it's
the
32
header-
bytes times 1, 2, 3, 4, 5, 6, so it's 6
So at
times
least
3.
5 times that.
Right, 5 times that.
Wow,
Okay? Right, it's 5 times that.
okay.
Okay? So we got a type of service field, which we're still figuring out how to use. Total length. We're going to use this for fragmentation. I'll show you how in a minute. The don't fragment bit says if you get this packet, it's too big for you to forward, and you need to fragment it, don't. Send back an error message. Okay? We have a time to live field. Remember I said the routing algorithms, they don't get the same data, could create loops. The loops can last for hours,
So they
days.
last infinitely, that's the.
Oh, yeah, right. I mean, and just because you do another routing update doesn't mean you're gonna get rid of it. Okay? So what they put in, because it's real hard to detect, I mean, back and forth might be easy to detect, but loops that involve more than one node can be really hard to detect. So there's a count, we would set time to live, but doing time's really hard. It takes a lot of, processing to really figure that out accurately. So it's really a count field.
Like hops.
It hops. And every time it goes through a router, that field is decremented by 1. When it reaches 0, the packet's thrown away if it's not at the destination.
So this is just like an impossibly high number, where it's like if you've done 10,000
Well,
hops,
it's not
that doesn't-
impossibly
you've done-
high because it's.
Not
one
impossibly
byte.
high, I'm saying
But it's-
possibly for
It's
a
1 byte.
normal. No, but I'm not
So
saying
it's- the
impossible
maximum
as in
value
like
is 255.
infinite. I'm saying impossible as in like a normal transmission between
Yep.
2 points. It's impossible for you
Right.
to exceed that.
Yeah, now, the general idea today is that the diameter of the network is about 15 to 20 hops.
The entire internet?
Yeah. Okay, so you might see people put 20 or 25 or 30 in it. A lot of nodes, and I've looked at this, just put 255 in it and don't worry about it. Okay? Okay, so we got a hop count. Then we have a protocol ID field. This is to identify the protocol in the layer above.
So you can find out how many hops, if you can catch it on the receiving end, you can see how many you went through.
Yep. If you know what the value was you put in to begin with.
Yes.
We said most of it's 255.
Well, but not everybody does the same thing.
Okay.
When you do tracer,
Huh?
when you do tracer, I mean the command line, tracer. So
Trace route?
Trace route, yes.
We haven't got there yet.
So I mean the
We're not there yet.
the
Alright.
recounted, yeah.
Yeah, we'll get there. Okay. So anyway, so now we have a protocol ID field that identifies the ID, identifies the protocol that we're encapsulating.
You mean like the application of us?
No, like it's TCP.
Oh.
The immediate data field. Okay, now, if you ask anybody on the internet what this is for, they'll say, well, it identifies the protocol. Well, not really. Because I can't have two TCP implementations being fed by one IP and have two different values of protocol ID field. It really is the type. Really, what it's there for is to identify the syntax of the encapsulated protocol.
Isn't that part of the protocol?
No. No.
Library.
This is it's there to identify the syntax of the data.
But I'm saying that a protocol in general is just, it's an etiquette saying how you're going to communicate, and that's saying how
Well,
that's
no,
going to
if you do an
communicate.
IP implementation, you do this, period. That's the syntax.
But the data is whatever's higher up in the stack.
Right. Well, higher up is what is encapsulated by the header. In the packet,
It's the payload.
yes.
And why would the protocol know what is in the payload?
Well, because it's not supposed to,
Right.
but they didn't know any other way to solve it. Because see, I could have TCP, or I could have UDP, or I could have SCTP.
Those are all the ones that are sitting up above IP.
Right. Okay, and at the time, they didn't know how to solve that.
So they actually know who it
Right.
is.
It was a big question early on if this wasn't a protocol violation or a layer violation. And the answer is, yes, it is. Okay? And like I said, if you ask them, they would say, oh, it identifies the protocol. Well, it doesn't. It really tells you what syntax you're going to use to decode it when you get there.
So when you're sending a packet in the packet type of service SCP,
Yeah.
they plugged it in there.
Yeah, there are codes assigned for all sorts of things.
Okay.
Now, that said, same thing. If you remember, in the MAC header we went over last week, there was an ether type field that did the same exact thing. Okay, these are a bad idea. If you go back, which we did some months ago, and because we had to look up for an ether type, and you look at the assigned ether types, it reads like an archaeology of the land industry for the last 30, 40 years. You go, especially for an old guy like me, oh, I remember those things, Oh yeah, are there any of those left? Stuff like that, But, because once they're assigned, you can't get rid of them. So having self-configuring protocols is a real advantage. This one isn't. Then we have a checksum over the header.
Is that a checksum of the header or a checksum of the payload?
No, a checksum of just the header. Okay. The theory here is that the higher layer protocol will check the veracity of the data. But all we're worried about in IP, because it's got to be really fast, is are we going to deliver it to the right place? So we check the header to make sure it's good.
That's a lot of digits for a checksum.
I'm sorry?
That's a lot of bits for a checksum.
16?
Like a
It's real bad if it goes to the wrong place.
Are there any redundancies in the checksum?
Well, remember, it's a checksum, not a CRC.
So it's like a
And
digest.
Well, it
it's
should
really
be one
fast.
bit.
I mean, it's a once complement thing. And you're only doing it over, what do we figure? 5 times 32 is 160 bits, right?
You do this with every packet,
Every packet.
it's a lot of overhead.
It's all in hardware.
You ain't seen nothing yet. Tells you what's going on.
Yeah, and this is version.
Well, not only that, but remember, we're also decrementing the time to live field, right? There's actually an algorithm for how to decrement the time to live field and update the checksum without recomputing it.
Isn't that hardware magic thing where it's like it's
No,
happening?
you can do it in software.
Okay.
Okay, then we have two 32-bit addresses, IP addresses.
One big packet so far.
That's the packet. Okay? Now,
That's the header.
that's just the header. That's just the header. And then we can have 0 or more words for options. Yep.
The destination address, that's just going to the IP address for a building. It's not necessarily saying the MAC address of the device in the building.
It is to the computer interface.
Okay.
No, it's It's not to the building.
Okay.
It's not even to the host.
It's directly to this device.
It's to the interface.
Okay.
Right. We don't know about buildings, we don't know nothing except cracks,
Okay.
okay?
So that just gets you to a machine up to a certain level, and then there's the protocol which says up to the actual level above that.
Well, first we have to do the transport layer, which is coming up in a few weeks, to make sure that that we have all the packets in order and none of them are missing. Right? And then we hand it to the application.
So somewhere higher up is the actual like port to the application.
Right,
There could be 30 of them waiting there at the
Yeah.
destination.
yeah.
So it's not in here.
Nope.
That
nope,
0 to
nope.
31 is not in this header.
No, we don't know about applications here. All we know is this is the interface it came in on, and actually this.
Yeah, because only the level above really cares about the application to
Right.
farm it out. Okay.
Okay? This is just getting it to in fact, getting it to the interface is wrong. And we'll come to that next week, or week after next. Okay, now we can have options in here too. And we can throw all sorts of things in here. Trace route that he wanted to have was an option that we can put in there, and every time you go through a router, it records in the header the IP address. Okay? We can have source routing, where we have an option that says, we want you to go through these routers to get to the destination. And we have strict source routing and loose source routing, where we say, you actually have to go through these routers in this order, or you can get there any way you want, but on their way between A and B, you need to go through these routers. We can have timestamps, we can do security, we can do all sorts of things. All of them are options in IP.
It's still in the header, correct?
Still the header.
So this is on the network layer,
This is all network layer.
and so this is a standard that like every country, every machine manufacturer agreed to?
Yep.
How did, that seems like a,
Well, in this particular case, they didn't have much of a choice.
okay,
IP was separated from TCP in 1978. The internet grew after that. If you wanted to join the internet, you did this,
right,
okay? And it was never gone through the usual standards process.
it was just like the internet protocol, like, in order to get on this network, you need to use.
Yeah, right, you just do this. Okay? All right. So anyway, basically what we're gonna do here is, we start out with IP gets encapsulated in 802.11, it's sent over to this next access point router, which, gets de-encapsulated, goes up to the IP process looks at the destination address, says send it over to this guy, so it goes down to this MPLS guy here who encapsulates it in his protocol, sends it over here, gets de-encapsulated, he looks at it again, of course he's decrementing the time to live field and all that stuff. Says, oh, it's supposed to down out this port, so it gets encapsulated Ethernet, comes over here and goes up there.
These are all the places saying, where do you want to go? That's
Yep.
not me. And we talked before in the other class how it
Right.
says, this is a destination router, and then it says, that's not your final destination, that's just to me.
Right,
Okay.
right.
Okay.
Keeps going along. We can do tunneling where we actually take an IPv6 packet. Not everybody understands IPv6 yet. So we encapsulate it in an IPv4 packet and we send it over and so on. We do tunnels. And of course, he likes this because he gets to bring in, the channel. And actually what they're doing here is actually not quite right because they're missing an opportunity. Because what they should be doing is not just encapsulating the data packet, but they should be reinstantiating the routing as well. So that if you do that, then you can actually keep smaller router tables because, if I, at this green level up here, this is, oh, there it is. This is one hop from here to here. So this is one hop, but then these hops are a different routing regime down here. Okay? And one of the big problems we have, and we'll talk about it a little later, is router table size. Okay? Now, IP fragmentation. Here's how it works.
Before we go into this, I just have one
Sure.
broad level question. This is all, you have to change slides. This is all done like the sixties and seventies, and we've learned a lot since then. Have they ever gone back to this and said, you know what, let's just kind of throw this out and start fresh now?
Oh, no, we can't do that.
I know the telecommunications.
Starting in 1978,
He's
the internet was too big to change.
It just feels like a lot of these problems are
Oh, no,
based on.
no. Actually, this is close to about all everything you need to do, to minimal you need to do. There's nothing there you can really throw away. There's some things you can do to improve. But what I just, pretty much,
Just
all
a
that you
classic.
need to do.
The acronym MPLS, what is that again?
That's just another network technology, don't worry about it, we're not gonna worry about it. That was just to show that you go in and out of different technologies with IP, and it was independent.
Yeah, what is it?
Okay, so let's talk about fragmentation. Now, there are two ways of doing fragmentation. We can have transparent fragmentation, where I go into this network and it gets fragmented into a bunch of packets because the minimum packets or the maximum packet size is smaller. And so, but when we come out, we put everything back together. And then we forward it on, and then we come to this one, and he needs to fragment it again, but into bigger ones. So, you know, he fragments it, and then it gets put back together. Of course, this has the problem that everybody has to exit through the same router, or the same gateway between two networks, right? Otherwise, it's not going to work. Then you can have non-transparent fragmentation, where everything gets fragmented here, and then you don't try and put it all back together. You just send it all forward, and it might get fragmented yet again, and then at the destination, you put it all back together.
Yeah, would be not right.
And that's non-transparent, and that, you know, there, they don't all have to leave by the same gateway. They can leave by different ways as long as they all ended up at the same place.
So the destination does that,
And the
the actual destination.
the actual destination, right, the destination address.
How does it know, isn't the router the one that fragmented it?
Yep,
Okay.
so how does he do that? Okay, so suppose, here's our packet, nice short one. It has a packet number, a packet identifier, remember that packet identifier field, of 27. It has the number of elementary fragments in the packet, which is 0. Is this the last packet? Yes, it is, we haven't fragmented it. So this is, you know, this is the end. So it's set to 1, and there's the rest of it. Now, we get to somebody, and he needs to fragment this for some reason. He can only send this much. So we send the same packet ID and IP. This is number 0, and this is not the last fragment. So that's a 0. Okay? We come down here. Now this one has the same packet ID, and this is an offset that says this packet starts 8 bytes after the last one. So count 1, 2, 3, 8. Put 8 here. This is the last one. So that's a 1. Now this gets forward. It gets fragmented again, right? So that one is 27, 0, 0, still 0. Now this one is the new one. It gets 27, 5, 1, 2, 3, 4, 5. He's not the last one either, so he's a 0, 2. Come down here, and we get 27, 8. He's still the same distance from the beginning it was before. And this is the flag is the last one. Now we have everything we need to know to put them back together. Right? Just one thing. This doesn't work. Never has. In the 40 years that IP has existed, it has never worked. Consider the following. As we'll see with TCP, each packet needs a unique identifier to know what fragments belong with which packets. At some point, the packet is broken into n fragments, and there's a probability p that at least one fragment is lost. The fragments that do arrive must be held for at least one maximum packet lifetime, which, but IP doesn't do retransmissions. As we'll see, transport is going to retransmit the packet after one round trip time plus a bit, because he hasn't gotten an ACK, and hand it over to the network layer, which the network layer will dutifully assign a new identifier to it. It's a new packet, right? To IP, it's a new packet. And send it. Go to step 2. See what happens? Now, the destination has to hold this for 5 seconds.
Is this the same as looping? Where it thought it was
No,
like a new-
router loops are a whole different matter.
No, not router loops, but the bridge thing where it's like it thought it was a new packet every time.
No, this is a whole different whack. So basically what's gonna happen is the destination host is gonna have a partially reassembled IP packet. He's gonna have a lost fragment from it that's never going to arrive. And he can't throw it away for 5 seconds. Within about at least 250 milliseconds, TCP is going to retransmit the whole thing, which is going to get fragmented again. And one of them might get lost. And now he'll have 2 copies, but he has no way to know that they're 2 copies of the same packet. And it happened a 3rd time, and a 4th time. And well, maybe after 5 seconds, the oldest one gets thrown away, you can reclaim that buffer space. But in the meantime, lots of nasty stuff can happen. However, there's a patch. Okay? It's called Path MTU Discovery. Okay? What we do is we send an ICMP, which is a IP sort of error message packet, or we send an IP packet with a maximum of the packet length with the don't fragment bit set. If this is too long on this path, we get back an error message. Packet couldn't be fragmented.
You would try to send it all the way to the destination.
Right, it tries to send it all the way to the destination. If you can't, if it has to be fragmented, it has to come back. So, okay, fine. So then he tries a shorter packet. So it's a new IP packet with the don't fragment bit set, but it's shorter. And eventually he figures out what the minimum packet, maximum packet transmission unit is for this path.
Does he do that before he even makes his first send, or does he do it when he doesn't get an app?
Well, he does it. No, he does it before he does anything. Okay?
So every time you're
Opening a new connection.
you size up the route.
First time, right? Only one time.
Yeah. Well, depends on how many iterations it takes.
So that's a lot of traffic, huh? All the time.
Right? Right? This is the equivalent of, Doc, it hurts when I do this. Well, then don't do it. Okay, there's just one problem. This doesn't work either.
But wait, there's more.
Many sites block ICMP because they're a DOS attack vector,
What's a DOS versus DDoS?
denial of service.
But what's DDoS then?
Denial of service.
DOS.
One thing to keep in mind is that PDU size is a basic parameter of the layer. Moving toward the backbone, it should get larger, so we really shouldn't see fragmentation going in, but we might, actually we might even aggregate them, but coming out, we should still have the same max packet size. So really, this, we should be building stuff like this. We aren't. And this is still a big problem in the network. Okay? Now, IP addresses. This gets real important, guys. Okay, Originally, IP addresses were flat, and there were four kinds: A, B, C, and D. And, you know, basically they were divided up into a small number of networks and lots of hosts and so on, okay? Obviously, you know, a Class A address was a really huge network. Class B was sort of medium size. You split it in half, 16 for network and 16 for host. And then for really small networks, which is really too small, 255 hosts is not very many at all. Okay, and then they had that E for future use. And here's the kind of thing, at the beginning, we were really loose about handing out Class A addresses. Bolt, Beranek, and Newman out here at Fresh Pond, who built the ARPANET, had 5 of them. They never had more than 5,000 employees. So, I mean, it was a little overkill. They've given them all back now. But, you know, if you look around, you can see all sorts of people. There are companies in that list that, you know, don't exist anymore. Those have been reclaimed.
Can you go back a slide? I'm sorry.
Huh?
Can you go back a slide? So, what are the ranges in the Class A? I mean, we're talking about.
Well, we're
100
talking
million?
about, what, 1 byte's worth of network, 255.
But I mean, what is that in relation to number of IPs, that Class A network?
24 bits,
Okay.
2 to the 24th.
Thank you.
Okay? Okay? And, you know, and there are DoD networks there that probably shouldn't be considered on the public internet at all, right? I mean, like, crazy.
Why shouldn't they be on the public internet?
Defense Intelligence Network should be on the public internet? No, I don't think
They're
so.
already in my phone.
Shall we?
Somewhere on here is the UK Social Security System's got a Class A. MIT has a Class A. And so on. Okay, so, yeah, then there are special ones for this host and the host on this network, and, you know, all sorts of funny things. Then, around 1990, we had the first addressing crisis, and I'll have more to say about this in the next class. There were 3 problems: exponential growth of the router tables, naming the node to solve a multi-homing problem, and impending shortage of IP addresses. They were handing out IP addresses in order. Okay? Do you realize what this means?
Sorry, can you repeat?
They were handing out blocks of IP addresses in order. So if somebody from, say, Paris came and asked for a block of IP addresses, he got block X. If the next person that you came was from Sri Lanka and asked for a block of addresses, he got X plus 1.
It's very easy to trace.
That meant that every time a block of addresses was handed out, a new entry had to go in the router tables.
It's not a specific.
How do you know where it goes? You can't assume they're not location dependent, right? You can't assume that because 2 addresses have numbers close to each other, that they're near each other, right? So router table growth, in 1990, we were up to 200,000 entries in the router table. And it was going like this. Okay? They took some immediate steps to moderate the problem. First was create private address space, and we'll talk more about that in a bit. With Jay, basically what we found out was you didn't need, not everybody needed to have a public IP address you could connect to. In fact, most everybody didn't need one. You were connecting out, you were not acting as a server. So giving you a private address had 2-fold advantages. 1, you couldn't be attacked, so you couldn't connect to you. And 2, we didn't have to use as many IP addresses, right? In the late 1980s, if you opened up a new laptop, it took about 10 seconds for it to be attacked. Tighten the rules for handing out large blocks of addresses. Refer most everybody to the tier 1 providers. Instead of giving everybody going to IANA and getting a block of addresses, go to your provider and have him give you a block. That way, at least we know what the prefix is for a provider like Comcast. And if you're on Comcast, you've got one of their blocks. All I have to do is route it to Comcast. I don't have to know where you are. Give tier 1 providers large blocks of addresses for their customers. Allow addresses to be aggregated. move to classless interdomain routing. So basically what we did, and then recommend a replacement for IPv4 to deal with the shortage of address problem. Now, what we did with CIDR, classless interdomain routing, was rather than having class A, class B, and class C, we said, no. We can set this boundary anywhere between network and host. So we don't have just, the difference between 255 and 65K is huge. So we can set this here. I can create a subnetwork mask and apply the mask by ANDing it to the address, right? It's a mask. And that will give me the part I'm going to route on. Okay? And, I can have, small numbers, I can have networks with smaller numbers. And so I use that as my routing entry, is just the prefix there. Okay? So that says that I can split an IP prefix into separate network subnets. So here I have, nobody thinks ahead in the internet. Back before all this happened, they decided they were going, system programmers are, diva bunch of people. We're going to express IP addresses as dotted decimals. So we're going to represent each byte in a 32-bit IP address by a separate decimal number. So this is 128.208.0.0. Okay, so that means that byte 1 is a 128 in binary, and byte 2 is 208, and so on. Now, what you can do now with the mask is say, I'm going to mask the first 2 bytes. He can represent all of those over there, and they have different parts of the address. This guy has got 96 and 0. This guy has got 128. Actually, I can't do 96. 128 is going to be a byte of 0 at the bottom, and then 5 bytes. No, wait, 7 bytes, 7 bits of 0 in the next byte. Right?
128 is.
Yeah, 128.
0, 1.
Yeah,
and the rest
yeah,
of zeros.
yeah. So if this is a 128, it's going to be 1. So and that's this one. So now, and that one can be a 128.00/18, which is the number of 1 bits in the mask. So now, if these guys are off over here, and these are all departments within this university, all I need to know to route to this university is it's a 128.208. Anything going to 128.208 goes to those, goes there.
And
Okay.
then they'll figure it out from there.
Right, and they'll figure it out from there.
So that's the
If I
only,
give them the final address.
Yep.
so that's the only thing that has to be out on the routing tables to the right.
To the right. Exactly. Right? And so we can set up, IP addresses with different number of assignments like this. Now, I think, I'll have to check. I've got some cheat sheets. I think I may have posted one. Let me see if I did, because you're going to be doing homework problems and stuff with this, and you're going to, why they didn't use hex, it'd be so much easier if this stuff was in hex. And so the same thing goes on, over distances, in New York, London, and all these guys in Cambridge, Oxford, and Edinburgh, look like a 192.24. And then when I get to London, it's a 192.24. So London has 3 router table entries for those, but New York only has to have 1. Okay? This is what's going on here. Right? The old New Yorker cover. New Yorker's view of the world. Up close we have good detail, but out there we don't know anything. And that's basically what we're doing with these things, right? So aggregation is pre-processing the network graph relative to this router to create a new graph with fewer nodes. Sets of addresses are being aggregated into a single node in the new graph. The routing algorithm is then run on this new graph. This works because all the aggregated addresses would have been forwarded to the same next hop anyway. The graph that each router runs the routing algorithm on is potentially a different graph. Okay, so what we want to do is look for the longest matching prefix routing it to the New York router. So we start in San Francisco, and we see 128.24.0, 128.24.12. So anything, we look for the longest one we can match, which is going to be 12. We send those that way. The others we send this way. Placement of operation of a NAT. Okay. So we want to have network private addresses and network address translation. So what we're going to do is we're going to punch 2 or 3 holes in the IP address space, and we're going to reserve them for private addresses. One of them is net 10, the old ARPANET address. Okay? And we're going to say, and no. And the others will be public, so we'll say, okay, these private addresses will never appear on the public internet. When these guys over here go to set up an address, they'll be assigned net 10 addresses. In fact, I'll bet if you go home and look at what when you're connected to your local Wi-Fi network, you've got a net 10 address. Your printer's one, and so on. And so you'll open a connection to net 10 to a destination address that's outside, somewhere over here. Okay? It'll hit this NAT box. The NAT box will record your private address and your destination port number. Okay, now we haven't talked about ports because they're up in TCP, but remember in the IPC model, in order to have multiple connections between the same 2 places, we had to have a connection ID, and we concatenated the ports to do that. So we're going to record that connection, and we're going to assign the source port and that address. We're going to keep a table of that and map it to this address and a different port. Now everything coming out of that NAT box is going to be coming from that address, but different ports. Okay? Now when he says, sends a TCP connect out here, and the guy responds with a connection, it's going to come back with this destination address and this port number. At which point the NAT box is going to translate that into that address and that port number and forward it on to you to set up the TCP connection. Okay? And so, basically this is how it's going to look like. We'll have a company router, and I have different addresses. The NAT sometimes doubles as the firewall. Now, NATs were really, really controversial. People yelled and screamed about them for, probably a good 10 years, and they're still yelling. And people would say, well, everything's under a single address space. Well, first of all, everything should be under, most sites don't want every address to be global. They like the idea that every secretary that can't be, attacked just by having an IP address. Makes the internet more connection-like. It's an artifact of the fact that your addressing architecture is broken. Violates layer. So does the protocol ID. That doesn't bother you. Forces use of TCP and UDP. Not really. No matter what protocol is on top, it'll have to have port IDs, or you can't have multiple connections. Okay? This one really kills me. Some applications pass IP addresses. Yeah, they do. And I have to help take the blame because I was in the room when we did it.
And
But for example, FTP has a command called port that is used for certain things, and it carries an IP address. And of course, you can't do that if you're behind a private address space.
This is also.
But on the other hand, what the heck is an application doing with a physical address?
May I ask you a question? What about dynamic port? How does it work?
Dynamic host reconfigured.
Port, dynamic port. For example, we know, right, when I use SFTP, when they negotiate,
Yep.
one dynamic port is creating,
Yeah.
and we don't have in routers.
They have an initial connection protocol that they do.
How does not solving this problem?
Well, they're trying to, but SCTP has its own problems. We need to stick to what we're doing here. I mean, what in the heck is an application doing passing around physical addresses? Right? I mean, you don't do this in a program, right? So this is just wrong.
That's just legacy.
That's legacy. I mean, we did that in FTP in 1973, you know? And then there's IP version 6. Guys, I'll talk more about this later, but this was really one of the most cathartic things that has happened to the internet. The idea was it was supposed to support billions of addresses, reduce router table size, simplify protocols, better security, efficient type of service, aid mobile casting, all these good things. It doesn't do any of it, except have more addresses.
Well,
Here's what an IPv6 header looks like. Notice the great amount of commonality with an IPv4 header. The only field they have in common is the version field. Traffic class, flow label, payload link, next header, hop limit,
It's the same as the,
time to live,
yeah.
and then 16 bytes of address. Okay? And then you've got the option fields. Think about doing source routing with 16-byte addresses, where each one of them is, they're all in the header. I mean, there are problems right now, and then you have packet fragmentation. I mean, one of the things they still don't know how to solve is, suppose you've got all these options in your header,
You have to break up all the header stuff.
and you have to break it up, but all the options won't fit in one fragment. Okay? So there are hop-by-hop options, destination options, and now those things have to go in a particular order. Fragmentation's been moved to being an option, which is good, but still a lot of unanswered questions here. And they're done much the same way they were in IPv4, where you have essentially a linked list of these things, and each one points to the next one. There's an offset, each one has a link, you know how big it is, so even if you don't do the option, you know how to skip over it. So, what are the advantages of IPv6? More addresses. Well, actually, that's true, but really, we're only routing on the first 64, not the whole thing. Header simplification. Well, that's 2% of the problem. Better option support. Actually, we've got a little problems here. And not only that, but options are always handled by the slow path. So, everybody tries to avoid, having packets go through the slow path to begin with. Improved security. Actually, it's the same as IPv4. One of the ground rules for IPv6 was anything you do, different with IPv6 has to work with IPv4 in case we have to back it out.
They did the same thing at Ethernet though, didn't they? It's all backwards compatible.
Yeah, well, it has to be backward compatible. So all this talk you hear about IPv6 has better security, better class of the type of service stuff, it's not true. It's the same as before.
Same.
Huh?
Same.
Yeah, same.
Same but different.
Yeah. It's not addressed the real problem of router table size. There's nothing in V6 that really addresses the router table problem. And in fact, if anything, the larger addresses are going to make the router table sizes even bigger. Transition requires a NAT once you're behind in that, what do you need IPv6 for,
Yeah,
right?
yeah.
No real problems with adoption. Actually, the real problem with adoption is that people now point to and say, well, gee, if we make another big change to the network, it'll take, look how long it's taken to adopt V6. Well, the reason is, this was pointed out almost immediately after V6 was approved, was IPv6 does nothing for the guy who has to pay for adopting it. So why does he do it? Okay, so the reason IPv6 has taken so long is because it had no advantage. It didn't do anything that would, save you money or reduce your costs or anything. This was great.
No problem.
The first version of IPv6, no private addresses. People yelled and screamed, and they put it back in. Then he took it out again, and they put it back in again. Like I said, this is going back and forth several times.
Who's getting so emotionally attached to this?
Well, the purists don't want private addresses. And the pragmatists are saying, we want private addresses because it's at least a first line of defense and security.
But
If you can't address it, you can't connect to it.
It's too fast, Christian.
so,
I was gonna say, like, there's some committee
Professor,
somewhere.
question.
Oh, no, this is an element of pounding tables.
how private addresses communicate with outside environment? Does they communicate with outside environment or?
No. Private addresses are never routed in the public internet.
So why they are arguing? Having
Well,
the private-
because it should be all one address space. The purists are saying there should be one big address space, right?
But if they don't communicate what's outside, why they need it?
Well,
They
see,
can
they think that this is the purists.
Uh-huh.
They have this, to them, IP is the sacred thing. Actually, it's a big mistake, but that's okay. We'll get to that later.
Okay.
But, to them, having a single address space that you can reach everything, okay, is important. Actually, we've shown that you don't need a global address space at all,
Okay.
okay? And so basically, the ITF has resorted to spin. There are all sorts of things about this, and I'll talk about that later. Fragmentation doesn't work. Header extension options don't work. They're putting the MAC address in the lower part of the IPv6 address, which makes a security problem, and it's just bad addressing practice, as we'll see next week, or 2 weeks. Using MAC address makes the route dependent. Can't route anything greater than a /64. MTU discovery doesn't work. Interaction of options and fragmentation, I mentioned. Will routing scale to 4.3 billion IPv4 addresses? We barely know how to deal with one IPv4 address space, let alone 4.3 billion of them. There's also something called ICMP, the Internet Controlled Message Protocol. This is just, you need to have something that will send back an error if IP runs into trouble. And so here's the kind of thing. This is where echo, ping, and all that stuff comes up. All these things, happen here. Here's ARC, Address Resolution Protocol. This is the problem we have with LANs, right? If I want to send to you and find out your address, and you're on a wire, I send you a packet, so send me back your packet. I get your source address. Well, how do I find out what MAC address maps to what, IP address if they're all on this one cable and everybody hears it? So we have to have, this address resolution protocol where I can send down and say, send me your MAC address and your IP address so I know what the mapping is. Okay, so I can then send, things to your IP address or your MAC address. Otherwise, I don't know how to do it.
Just like flooding.
No, it's not like, there's a broadcast, but it's down an Ethernet line, so it's really only one packet. Huh? From outside they block it. Yeah. Right. We'll talk about dynamic host reconfiguration later, or host configuration later. There are other internet control protocols. This is how we can use that. Intradomain routing, we have two fairly popular, link state protocols, ISIS and OSPF. Generally, people swear by ISIS, it's a lot more stable. The guy who runs our network, you know, will almost shoot you if you talk about OSPF.
So the guy that runs ISIS can shoot us?
Our network right here, yeah. He sent a video for me, for my advanced class, and, yeah, yeah, he's very good, he's very, very good. He's got a great, and sort of to make this stuff scale, we can define autonomous systems, which we're actually defining. I'm gonna leave this out for now, because we need to understand what's going on with the internet and why they had to do this, because this is really a kludge, because the internet is not an internet. That's another thing. We're not ready for that.
I'm not ready for this.
And so we can, you know, we can take this, we can define autonomous systems, we do intra-domain routing within this, and inter-domain routing across them, and that gives us a graph that looks like this. OSPF is a bit like link state. BGP is what we use in between. And I think I'm gonna quit it there. Okay, so we're done. At some point, probably before we go addressing, I'll talk about, the rest of the land stuff, but, I don't think any of that's gonna be on the exam, so it's not a problem.
No land stuff on these things?
Well, no, I didn't say that, I said none of the stuff I haven't covered yet.
We'll get the question about IP on the midterm.
Yep. Yeah, everything up through this lecture goes on the midterm,
Okay.
okay?
Do we have,
That's the bonus question, right?
Now, if things work out right, this means that tonight's homework will be due when we come back, and I'll be able to hand it back to you at the midterm.
Okay.
Okay, that's where it's time. Next week, we'll talk about naming and addressing, which is probably one of the more subtle and important topics in all of networking.
And homework, because of the break, is gonna be due our next class period, right?
Yeah,
Okay.
yeah, because of the break, yeah.
So this homework that is going to be assigned this evening is due when?
March 2nd?
At the,
3rd?
at the midterm?
No, it's due, it's due at the next lecture.
Midterm is the next lecture, isn't it?
Is it?
No, the
That's
next
the
time we
last
meet is
lecture
the midterm,
before.
or is there one more?
There's one more between now and the midterm.
Oh, there is.
I think so.
So the midterm's after spring break?
Yeah,
Okay, perfect.
are we
Yeah.
meeting next week?
Oh, I thought spring break.
no, we're not meeting next
Nope,
week.
7th through
So
14th.
March,
March 7 to 15.
yeah, next time we'll be on TC, I'm back in our old room, okay, and, yeah, which is what, like March 3rd?
Yeah.
Yeah, March 3rd.
Yeah, and so we'll meet then, I'll talk about naming and addressing.
Sure.
And
Naming and
we'll
addressing.
be-
We break is the 7th.